So we're going to look at indeterminate products and indeterminate differences. So the first example is the limit as x approaches infinity of x to the third times e to the negative x squared. So this is a product. The x to the third is approaching infinity, but e to the negative x squared is approaching 0. So we have something really big times something getting really small, and this is called an infinity times 0 indeterminate form. So we cannot apply L'Hopital's rule because it's not a quotient, but we can rewrite it as a quotient. So we rewrite the product as just x to the third over e to the x squared. And now we can see that we have an infinity over infinity indeterminate form. So we can apply L'Hopital's rule. L'Hopital's rule says that this is going to be the limit as x approaches infinity of the derivative of x to the third over the derivative of e to the x squared, which is e to the x squared times 2x. Remember, that's the chain rule in the denominator. All right, so now this can be simplified a little bit. It's the limit as x approaches infinity of 3x over 2e to the x squared. Now, we can see that the numerator is getting arbitrarily large and the denominator is as well. So we have another infinity over infinity indeterminate form. Well, that's not a problem. Notice how things have progressed a little bit. The power in the numerator has gone down a little bit. So maybe if we do it one more time, we'll get rid of the problem. So let's do L'Hopital's rule again. We get the limit as x approaches infinity of the derivative of 3x over the derivative of 2e to the x squared. So it's 2e to the x squared times 2x. And if we simplify it a little bit, we get the limit as x approaches infinity of 3 over 4e to the x squared. And now we can see as x gets arbitrarily large, the denominator is getting arbitrarily large. The numerator is just 3. So this thing is approaching 0. So the limit is 0. All right. So when you have an indeterminate product, infinity times 0, it's really easy to just rewrite that as a quotient, either an infinity over infinity quotient or a 0 over 0 type quotient. All right, let's look at an indeterminate difference. So let's look at the limit as x approaches 1 of x over x minus 1 minus 1 over natural log of x. Notice that the first fraction, the numerator is approaching 1 and the denominator is approaching 0. So that's getting arbitrarily large. And then the other fraction, the denominator is approaching 0 as well. So that's also getting arbitrarily large. So this is called an infinity minus infinity indeterminate form. We have something getting arbitrarily large minus something else getting arbitrarily large. We don't know if that's 0 or some positive number or even some negative number. We don't know what's happening. Or it could be infinity. It could be unbounded. So we have to figure out something else. So what we're going to do is we're going to rewrite the expression as a quotient. And hopefully the quotient will either be a 0 over 0 quotient or a infinity over infinity indeterminate form, and we can use L'Hopital's rule. So what I'm going to do is I'm going to rewrite it using least common denominator. So it's going to be the limit as x approaches 1 of, and now my denominator is going to be x minus 1 times the natural log of x. And the numerator will be x times natural log of x minus 1 times x minus 1. So now let's look at this. If we plug in 1 in the numerator, we're going to get 1 times 0 minus 0. So we have a 0 over 0 indeterminate form. So L'Hopital's rule says that this is going to be the limit as x approaches 1 of the derivative of the numerator over the derivative of the denominator. So in the numerator, the derivative of x times natural log of x requires the product rule. So it's going to be the first times the derivative of the second plus the second times the derivative of the first minus the derivative of x minus 1, which is just 1. And then in the denominator, we have to use the product rule. So that's going to be the first times the derivative of the second plus the second times the derivative of the first. All right, and if we want to simplify a little bit, we can rewrite this as the limit x approaches infinity of 1 plus natural log of x minus 1, so it's just natural log of x, over 1 minus 1 over x plus the natural log of x. All right, so now if we try to plug in 1, we see the numerator is going to be 0 and the denominator is going to be 0. So again, we have a 0 over 0 indeterminate form. So let's just use L'Hopital's rule one more time. So L'Hopital's rule says that this limit is going to be the limit as x approaches 1 of the derivative of the numerator over the derivative of the denominator. And so the derivative of 1 is 0. The derivative of negative 1 over x is positive 1 over x squared. And the derivative of natural log of x is 1 over x. So now we could simplify this, but if we plug in 1, it actually works. So plugging in 1, I get in the numerator 1 over 1, and in the denominator I get 1 over 1 squared plus 1 over 1. And the answer is positive 1/2. All right, so we've seen that L'Hopital's rule only applies to indeterminate quotients of type 0 over 0 or infinity over infinity. But we can get indeterminate products, infinity times 0. We can turn those into indeterminate quotients, and also indeterminate differences, infinity minus infinity. Those can be turned into quotients as well. We can get those into a 0 over 0 or an infinity over infinity indeterminate form. And then once we do that, we can apply L'Hopital's rule and compute the limit. All right, we're going to see a few more indeterminate forms and examples of how to transform them into quotients. Everything has to be changed to a quotient, and then we can apply L'Hopital's rule. So I'll see you in those videos.